Let us continue afternoon session. Second speaker is Professor Bracci from Italy. His title is Generalization of Camacho-Sad Index Theorem and Applications.
So, first of all, let me thank the organizer for inviting me to give this talk. It's really a pleasure, and especially for giving talk in this very nice place and dedicated to Professor Camacho. And what I'm going to talk is about some generalization of one very famous theorem, which is the so-called Camacho-Sad Index Theorem. And after Jean-Paul Brasselet's speech of yesterday, I can't refuse now to give this talk. So let me first of all recall the theorem, even if most of you know it very well. So we have M, which is a two-dimensional manifold, complex manifold, as a curve, which is compact and non-singular. And then we have a foliation F on M, which is a holomorphic foliation, and S is F invariant. Then, for any point P in S, there exists a certain number which I call a residue of F, S, P, which are complex number, also called indices, such that the sum of this number is equal to the first germ class of the normal bundle of S into M, which is the same as the self-intersection number of S, where this just a fixed notation. This is the normal bundle to S. And let me call this pi, this projection. Okay, so the generalization I'm going to talk about are essentially in dimension 2. I'm decided to give this just to try to be as simple as possible to explain the idea that I found underlying this theorem and some generalization that you can use to study dynamics of both holomorphic foliation and holomorphic diffeomorphisms. But I can't help mentioning generalization in several variables. And but first, the first generalization that, at least my knowledge, in dimension 2 is due to Alcides Lin's Neto, which replace M with P2 and S with an algebraic curve. Then there is a theorem by Tatsuo Suwa, where M is anything but S can be also singular. And then there are generalization to several complex variables, and let me. Then as I learned this morning, today at lunch from Jean-Paul Brasselet, it was the first generalization was probably by one of his students, Gmira Usha, and Jean-Paul Brasselet himself. And then still Alcides Lin's Neto. These were M as dimension greater, and S could also have greater dimension or codimension. And also there are then some major step is done by Daniel Lehmann and Tatsuo Suwa. And also let me mention a first quite simple case where M is not supposed to be smooth. itself, but as some singularity. And here there is a recent work by myself and Tatsuo Suwa. And of course there are many others work by Brasselet, and then I should mention also Pepe Seadi and many others. Just let me stop here. Okay, so this is just somehow a brief sketch of this kind of a generalization, where always S is supposed to be invariant. Then there are other generalizations where S is no longer invariant. So in this case, I think that the first one is by Camacho himself, where S is the zero section of a line bundle. And then there is a paper by Camacho, Movasati, and Sad, where they generalize to the case, well, here is but not invariant, where they generalize this result when S is so-called fiber embedded and 2 linearizable. I should also say that there is a result by Marco Abate, Francesca Tovena, and myself, where we have this same kind of results when S is that we call comfortably embedded. But I'm going to talk about this later. Okay, so this is more or less the kind of generalization that you can have about the Camacho-Sad index theorem. This is actually a different kind of theorem, of residue theorem, than the one which Tatsuo Suwa taught before. Because in this case, this residue can really be a complex number, not just an integer. And also it reads the embedding of S into the ambient space. Also in application, it's very important to compute a residue. I'm not going to write down the formula, but it's something that you can do. And in several, well, if the dimension is greater than 2, then this is not just a sum, but it's a sum in the homological sense using Poincaré and Alexander duality. Okay, well, now let me also give a brief proof of this theorem, which is not the original Camacho-Sad proof. It's a proof that I learned from Daniel Lehmann, and it is essentially based on a paper by Baumbot. The proof goes as follows. You first want to construct a 1-0 connection for the normal bundle of S outside the singularity of the foliation. So you can do this way. You have your foliation F, which is locally given by a vector field X, and outside the singularity of X, of F, sorry, X generates, is a basis of the tangent bundle to S, because F is invariant. So this means that essentially you have to define this, where S is a holomorphic section of the normal bundle. Since the holomorphic section generates as a C infinity modulo the section of the normal bundle, then this is enough. And then S, you can look at the projection of a section S tilde restrict to the curve S, where S tilde is a holomorphic section of the tangent bundle to M. So to define this, what you can do, you have your vector field X, which is defined, let's say here, restrict to S, X, which is defined everywhere. Then you take S tilde, you restrict to S, and then project down, and then you project down to the normal bundle. So doing this, you have a connection. This is just the holomorphic part of the connection. Then you extend in the usual way to an entire connection outside the singularity, and then you can use either the check-the-RAM cohomology, or even in this case, just a partition of unity to extend the connection to a connection of all the normal bundle, for all the normal bundle. And then what is important is that here you have the Jacobi property. And then for this reason, once you look to the curvature, then the curvature is 0 for this connection outside the singularity. So this means that this is your curve S. These are the singularity of the defoliation, and outside here the curvature of this connection is 0. So this means that the first Chern class, which is reads by the curvature, localize around this singularity, and the localization that you can compute, for instance, using Stokes' theorem or computing the both difference class, is exactly the residue. Okay, so why did I give this proof? Because from this proof you see that what is really essential for this to work is the fact that X is not defined on all of M, all in an open neighborhood of S, but it is just defined to some first order. So let me say better. Suppose that X tilde is another vector field which is equal to X up to some, let's say, T1 plus R2, where T1 are terms are vector given by, let's say, suppose that S is given by Z1, Z2, such that Z1 is equal to 0. So this is something of the form Z1 d over d Z2 times something, times another function, and this R2 is something of the form Z1 squared times some vector. So in a sense, what I'm saying is that this X tilde is your X plus something which is tangential to the curve and vanishing at order 1 on the curve, plus whatever you want, but which vanishing at order 2 at the curve. So in this case, if you do this computation, you see that the result is exactly the same, because you have a term T1 which dies when you derive by S tilde and you restrict to the curve, then it dies, or if you derive this S tilde when you restrict to the curve, it doesn't die, but when you project down, it dies. And the term of order 2, of course, they die when you restrict to the curve. So this is essentially the basic observation that you may want to do to generalize this result. I just want to mention, but I'm not going to say much, that you can rephrase all these arguments using sheaves, but in the sheaves language. But then you can well define what is the first order extension along some vector field, along some vector bundle, and so on. In the same picture, somehow you can also put the variation index theorem, but I'm not saying more about this. Okay. So, so now let me, using this philosophy, let me give you the two kinds of generalization. The first is about non-transversal S. So we get S, which is non-F invariant. Okay, so first of all, you see that the ingredient that you have here is that you have a vector field which generates the tangent bundle to S, which is a basis for the tangent bundle. So if S is not invariant, this means that this is S, and here is your foliation, which may be tangent somewhere, so on, can be singular, so on. And but here it is not, of course, tangent, so you do not have a way to give a connection, unless you can somehow project down this. In other terms, if you look to the exact normal sequence, what you want to do is you have a foliation here, you want to go here. So essentially what you want first is that this sequence splits, holomorphically, of course. And this condition is, thanks to work of Grothendieck and Thea, is a cohomological condition. This sequence gives rise to a class of cohomology, and the fact that it splits is equivalent to the fact that this class of cohomology is 0. So you have splitting. Let's call this split sigma, if you have. And then what you can do, you have your F, and then you can define F sigma, the projection of this foliation, to be, you restrict your foliation to the curve, and then you apply your splitting. So, but okay, so now we create, if we have these splits, the splits is a cohomological condition, so you do not have splitting in general, but you may have. Okay, so you have this new foliation which lives only on the curve S, and then out of this foliation it might be 0, identically 0. Well, in that case there is nothing you can do about this index. But if it's not identically 0, then you create maybe some new singularity doing this. But then you have a foliation on S, which of course in this case S has dimension 1, foliation has dimension 1, so it's not very exciting. Nonetheless, this foliation is defined, but it's defined only on S. And then you want somehow to extend, because you see from this proof of the Camacho-Sad index theorem, what you want is to have extension somehow of the basis of the tangent space to a neighborhood to get a Lie bracket and then restrict. Okay, so splitting it's not enough. You need another condition that I call comfortably embedded. And this condition here, by the way, implies the Camacho-Sad two linearizable condition. And comfortably embedded, it's a bit hard to describe easily. But let me just sketch this in this way. So here I have splitting, and here I have comfortably embedded. Then I have a cohomological condition for having splitting, which means that this exact sequence splits. You want this condition to split. And comfortably embedded means splitting plus the splitting of this sequence. Where this is the ideal sheaf of S. So it's ES cube, and then here we have the cotangent bundle. Okay. So this is the cohomological condition. Then you have also an algebraic condition. Algebraically, splitting means that you have the holomorphic function on S, then you have the holomorphic function, you have this sheaf, and you have a canonical map this way, and you want to have a lift this other way that make this to be the identity. So if you have this is equivalent to have a splitting. And from a comfortably embedded point of view, you have from the first infinitesimal neighborhood, you have still a canonical mapping to the second infinitesimal neighborhood, and you want to have a lifting of this. This is the algebraic condition.
Both curves in CP2 are comfortably embedded?
No, you need some condition on the intersection number, I guess. A rational, what was the story? Rational curves and with low, a rational curve with self-intersection number less than 0 again, I can't remember a number that they are comfortably embedded. For instance,
almost no curve is comfortably embedded.
Yeah, okay. The point here is that I'm going to talk about S smooth. I'm going to talk about S smooth, but if S, let's say this way, from the proof of Camacho-Sad theorem is the same if S is singular, because you just simply take out the singularity of S, and also you take out the singularity of F. So if you have an open Riemann surface, this is comfortably embedded. Stein space is comfortably embedded, any Stein space. So in particular, open Riemann surfaces are comfortably embedded, and since you essentially, when you work with this kind of theorem, you take out the singularity to create the connection, then this means that it works even if the curve itself is not, if you have a compact curve which is not comfortably embedded, if you take out a point, then it becomes comfortably embedded. So you can work. So I didn't want to mention about singularity by now, but okay. And okay, so finally the third, which in terms of local chart, so we have our S, which is given as Z1 equal to 0. And then we have an atlas this way, that if we, let's say, alpha, and here we have another atlas, Z1 beta equal to 0. Then here you have D, for splitting means that the derivative of Z2, so the coordinate along S of the second atlas with respect to the derivative respect to the normal direction belongs to the ideal sheaf of S. So it's divisible by Z1, and for comfortably embedded, what you have is that the second derivative of Z1 beta over the derivation about, well, okay, let's say this way. These belong to the ideal sheaf of S. So these are some equivalent conditions, and okay, so this means to be comfortably embedded. And so when you are comfortably embedded, you are splitting, so you can take your foliation here and take out a basis outside the singularity of your S. And then what you want to do is to somehow extend the foliation sigma at the first order around S. And you can do using exactly this condition here, because in that case, let's say if F sigma is given by just one, A of Z2 D over dZ2, and your F was given by some, let's say, A2. Here you have A1 D over dZ1 plus A2 D over dZ2. Then what you can do is to consider as an extension of this, given by A1 D over dZ1 plus A2, let's say sigma, D over dZ2, where this sigma here means that you essentially extend constantly along this fiber, along the normal fiber. So A1 of sigma of Z1, Z2 is nothing but A1 of Z2. Okay. Here you take the same, sorry. Okay, then if you do the calculation using this condition here, you see that you are exactly in this setting. And then you get the same Camacho-Sad index theorem for the non-transversal, for the transversal case. I wish also to mention that there are other kind of index theorem when you are in the transversal situation due to Marco Brunella and Onda. But they are not of the Camacho-Sad type. They essentially measure the number of tangential intersection. Okay, so this is
This way you obtain a flat connection on a vector bundle, on a line bundle?
yes, we obtain a flat connection on the normal bundle of S outside the singularity of F sigma. Because when you split, when you project down, you may create some more singularity.
And you get a resonant formula even if you delete some points.
Yes, exactly. I mean, if you have a compact curve which is not comfortably embedded, you can decide to take out one point, and then it is comfortably embedded, and you have a Camacho-Sad index theorem. But this point here becomes a point where you have to localize the class. So you have a residue at that point, even if there is no way to have it. Okay, so now let me, the second part of the talk, I want to talk about dynamics, because this is also a Congress of Dynamics. And doing this, I want to give a second generalization of the Camacho-Sad index theorem. So the problem now is completely different. At the first sight, it seems that has nothing to do with what I'm talking up to now. The problem is study the dynamics of a germ of holomorphic map from C20 into itself, fixing the origin. And of course, you look to the differential first. And then you take the spectrum, and the spectrum is lambda 1, lambda 2. And then if you are in the hyperbolic case, So if the two eigenvalues are of modulo different than 1, then the situation is clear, because either you have a basin of attraction or a basin of repulsion, or otherwise you have a stable and unstable manifold. So the dynamics is clear. And also you have topologically linearization in this case. Then the case more difficult are when you have one eigenvalue which has modulo 1 and the other maybe has not, let's say this way. So at first you can look when one of the eigenvalues is exactly 1 and the other is less than 1. In this case you have results that dates back to Fatou and Hakim, Weda. And then I wish to mention also Canil-Martins. We essentially gave a topological classification of this kind of mapping based on another nice results of Professor Camacho. And also, okay. So that essentially, and if lambda 1 is modulo 1 but is different than 1, then it depends, and you have the Bruno condition and results by, for instance, there are results by Peschel, which tells you that in some cases there may exist a Siegel disk and so on. So, but I'm not going to enter here. And so let me go to the case where lambda 1 is 1, and then you have also lambda 2 which is equal to 1. In this case, there are results by Ekal, Monica Kim, and Marco Abate, but also Fabio Brocero and Ribon. These are somehow of different kind. I mean, Ekal and Hakim proved that in this case, generically, there exist petals, where a petals is nothing but a germ of curve arriving to the origin, which is invariant for F, and where the dynamics of F is attractive. So let me give this brief definition. So this is essentially a holomorphic map from the unit disk to C2, a germ, this way, which is holomorphic and continuous up to the boundary. Let's call this delta. Continuous up to the boundary, mapping the boundary arriving to the origin, which is invariant by F. And where the dynamics is clear in the sense that if you take if you iterate a point, taking the limit for k goes to infinity, this means composition of F with itself k times, you go to the origin. Okay, so this is called petal, or also parabolic curve. And this result by Ekal and Hakim proved that generically you have a petal. Generical means essentially the same as in the foliation case, where you know that if you have a singularity, then by Poincaré-Dulac normal form, generically you have separatrix. But then you need the Camacho-Sad index theorem to prove that there always exists at least one separatrix, maybe singular through the point. So here the Ekal-Hakim result play the same role as the Poincaré-Dulac normal form. And they are proving in a completely different way. I'm not able to understand Ekal's work, while Hakim is done using Banach space technique. So he can construct this petal as a fixed point of a good operator. And then Abate instead proved that there always exists a petal, and his proof is essentially the same as the Camacho-Sad proof of the existence of separatrix, except that if you read the original Abate's paper, then you don't understand why it works. Okay, instead Fabio Brocero gave studies also the dynamics in this case, and they find a nice result in case the point is, let's say, dicritical. Now I'm going to say what it is, and also he has some topological classification of this case. And just to finish the picture, let me mention a recent result by myself and a PhD student of Roma, which is this one. You have lambda 1, and lambda 2, the modulo is 1, but lambda 2 is not 1. Then there is this result by myself and Laura Molino, which tells that we find some invariant, holomorphic invariant, also formal invariant. And we prove that generically, even in this case, there exist petals tangent to the eigenspace of the eigenvector, the eigenvalue 1. So, okay. Okay, now I want to concentrate to this case here and tell you how you can prove essentially Abate's theorem using this point of view that I mentioned. So using this generalization of Camacho-Sad index theorem that I'm going to show. Well, now I have to open a parenthesis, and which probably will like to Marco Brunella, which is about a philosophical guide that I have in this kind of problem. It's philosophically essentially because I'm not able to prove how to make it works, really works without no idea. The idea is the following. You have this your map fixing the origin where the differential is the identity. So what you can do first is to blow up the point, the origin, and then you get the exceptional divisor. And you also can blow up the map in such a way that it works like this. So essentially f tilde is your f outside the exceptional divisor, and when you restrict to the exceptional divisor, it acts like the differential, so it is the identity. So this means that f tilde restrict to d is the identity. Okay, so now you have a map and you have a curve of fixed points. And what you would like to do, the best would be to be able to associate to f a vector field in such a way that f is the time one flow of this vector field x. Unfortunately, you can't do this. At least you can do, but x is going to be just formal. It is unique, but it's formal. And now the point is, okay, you do this, and then you have a foliation, formal foliation around this curve, and this curve is singular for this foliation, but you can saturize, you can somehow normalize, so to make this vector field having only somehow isolated singularity on this curve, and then you can repeat exactly the Camacho-Sad, well, you apply Camacho-Sad formal theory in some sense, and you come up with a formal separatrix here, somehow, that project down somehow to some formal separatrix downstairs, and from here it is formal, but you can pick up some pieces which is convergent, and such pieces are exactly the petals. Okay, that could be a way to prove, but I'm not able to do because of several problems that I found. And also there are another motivation which is also serious for me. First of all, that once you do this step, it's very complicated. I mean, you can do in principle, but if you are given a map, it's very complicated to write down this. And also, if you start from a singular manifold here, instead of C2, you start from a manifold M, which has a variety, which has a singularity at some point, then in that case, I have no idea what formal could mean. And then, but even in this case, you may want to study dynamics. And indeed, this is something that I do with Tatsuo Sua. But we use a completely different point of view than this one. Nonetheless, it is good to have this picture in mind to be guided in what you want to prove. Okay, so now I give you. So if some of you has some idea how to work this way, I will be very happy to listen to. So, okay. Let me tell you instead my idea. My idea is this one. We have S, and then we take locally. We can consider locally a family of foliation whose time one flow approximate at the first order our F. We are in this situation here. Sorry, not S, but D. So this means what? That here, suppose that our D is given by, in this coordinate, Z1, Z2, as Z1 equal to 0. So I can consider this one form here, or morphic one form, Z1 composed with F, here we have F tilde, now okay, let's call F tilde, minus Z1 in the Z2, minus Z2 composed with F minus Z2 in the Z1. So this is a form, and it depends on Z1 and Z2. And it generates a foliation. When we take this equal to 0, we have a foliation that we can call F of Z1, Z2. Look, now F is the identity on D, so when you restrict to D, you have 0. So this is complete. D is a singularity for this foliation. But you can saturize this foliation. This means that you can divide by the greatest common divisor of these two guys, like this, say Z to some mu, Z1 to some mu. And then you have a foliation which has only isolated singularity on D. Okay, great. But there is a problem. This foliation depends strongly on the coordinates that you chosen. You have several ways to choose coordinates, so it depends strongly on the coordinates that you choose. But what you can prove now is the following fact, that it might be that D can be or cannot be invariant locally for this foliation. So if D is invariant, okay. If D is invariant for this foliation F Z1, Z2, then you say that F, your capital F tilde, is tangential to D, and except for the definition, what is important is that it is so for any choice of Z1, Z2. So for any choice of coordinates, such a way that D is given by Z1 equal to 0 and Z2 is the other coordinate. So the fact that it is tangential is independent of the local coordinate that you choose. If it's not invariant, then you call non-tangential. Also, what is important is that you can define the singularity of f tilde to be exactly the singularity of your f z1, z2. This set also is independent of the coordinates z1 and z2 that you chosen. So you have a good set, which are going to be your candidate for localization of the characteristic classes, and you have this kind of definition of tangential. Now, what is much more important, and I'm going to write here, is that if you take let's say x, a vector which generates one foliation, the foliation in the coordinates z1, z2, and let's say x at we generate, no, at is not, x check, we generate the foliation given by these two coordinates, provided z1 and z2 check are different, then you find that they are the same up to a term of tangential order 1 long S plus something of order 2. So this was exactly what you needed to perform this kind of proof. And then you get the Camacho-Sad index theorem even in this case. So let me write this theorem, which tells you that if, let's say this way, f tilde is tangential to D, then you can define residue related to f tilde D at point P, complex number, in such a way the sum of this residue is equal to the self-intersection number of D. So in this case it's -1. Let me say that with a different proof, this theorem is due to Marco Abate, and then myself and Francesca Tovena proved this for when D is as singularity, and then there is another kind of this result that we always use to get information about dynamics, and now I'll tell you in my last 10 minutes how to do this. But there is another result by myself and Tatsuo Suwa where D is a singular curve, but also the ambient space has some kind of simple singularity. In that case, I just wish to mention that even to define self-intersection is not that easy. I mean, you can use NUM for theory, but for this context, it's not exactly what you want, but it's okay. So now dynamics. So we have this other generalization of Camacho-Sad index theorem, and we want to use it for dynamics. So the first effect that you can see is that if the residue of f tilde d p is 0, then there is no dynamics. Near P. This means that this is your curve D, this is your point P. There exists a neighborhood of P in such a way that if you start with a point in this neighborhood, after a finite number of steps, you go outside the neighborhood or you go to the point P. So there is no asymptotic dynamics. In particular, there cannot be petals. Okay. The second is the following result, that if the residue f tilde dp is not a rational number or 0, then there exist petals, and you can also say the number of petals, but not going to say here, petals for f tilde at the point P. And for this, you need to use this theorem. And for this result, there are actually many proofs available from the first, the original proof of Camacho-Sad that you can repeat even in this ambient. Okay, I forgot to say something, but and then there is the proof of Juan Cano. And also I should mention Sebastiani. And for the local case, in the singular case, there is a result by myself and one student of mine, which is Degli Innocenti, where you prove results of this kind. Camacho-Sad, Cano, and Sebastian, of course, they work in the case of foliation, but once you have this dictionary, you can go to diffeomorphism and everything works. I said that I forgot to mention that also there is another, there are three ingredients in the proof of existence of separatrix. The first one is the Camacho-Sad index theorem. The second is Seidenberg theorem of resolution of singularity. And the third one is this the combinatoric and the Poincaré-Dulac normal form. So essentially what you do, you have a simple singularity where you know the behavior, where you know the dynamics of foliation, and in the same way, in this case, we have and in this case, we have simple, let's say this way, simple singularity also for map. And simple singularity, as you may guess, are exactly the simple singularity for your foliation F Z1, Z2. So you can also give the definition of simple singularity. At a simple singularity, you have petals. And this is essentially, you can rephrase in this way the work of Ekal and Hakim. And also you have the Seidenberg resolution theorem. And in this case, you can simply apply the Seidenberg resolution, the original Seidenberg resolution theorem for foliation. But you have to be a bit careful because once you associate a germ of foliation, then you blow up and you get a new germ of foliation upstairs, and this is not exactly the pullback of the downstairs foliation. It is the same up to the right order, and that's enough. But it's not the same, so you have to be a bit careful. But nonetheless, you can apply Seidenberg residue theorem. And then you can simply copy, if you want, the original proof of Camacho-Sad, or you can use a bit simpler proof of Juan Cano or the one of Sebastiani and so on, and you get existence of petals this way. Okay, I think I can stop here, but I want to finish with just a bit commercial. If you were interested in some of my work, you can find on my webpage, which is this one. Obrigado.
So, any question or comment? So, thanks again.
Thank you.
I don't know if you are aware of the